When we want to add many different numbers together, it's convenient to have a notation that saves us some space in writing that. For example, suppose we wanted to add a set of numbers a1, a2, a3, and a4. We could, of course, just write that sum as a1 plus a2 plus a3 plus a4. Or we could use the summation notation. The summation notation is based on the use of the Greek sigma, an uppercase sigma, which is an S, of course, in Greek. And one way of writing that would be to say that this sum S here is the sum from j equals 1 to j equals 4 of the terms aj. So that would be a1 plus a2 plus a3 plus a4. Or an alternative and completely equivalent notation would be this one here, where we listed the 1, 2, 3, and 4 on the bottom line. Or maybe we just might write this with the ellipsis in the middle. If the range of j is obvious and we want to save ourselves some writing, we might just specify that the summation is over j, and we already know the range of j that matters. J here is what's called an index, so the j on the bottom of the numbers here is an index. The same index is in this summation sign. Incidentally, the plural of index can be either indexes or indices, and you'll hear both of these used in math and science. For the index of a book, perhaps we only use indexes if we have several books with different indexes. But as I said, in math and science, we will also use this term indices. As an example of the summation notation, let's look at an arithmetic series. If we have a set of numbers that are spaced by some constant amount from one to the other, we can call that an arithmetic progression or an arithmetic sequence. And for example, we might have a way of writing this, which would be classic for the terms in an arithmetic series, where the nth term in the series is the first term in the series plus n minus 1 times the separation between the terms. For example, the numbers 4, 7, 10, and 13 are all equally spaced by an amount 3. And in this case, obviously, by definition, a1 would be 4, a2 would be 7, a3 would be 10, and a4 would be 13. And this number d is simply 3. So a1 is 4, and the next term has, the second term has 2 minus 1 here. That's 1 times d, that's 3. So we're adding 3 onto 4 to get 7, and so on. Now, when we add all these terms together, that becomes what's called a series. So when we take the terms in a progression or a sequence and add them together, we get a series. And in this case, obviously, if we add up these terms, simple arithmetic here, we get 34. We could also write that as the sum from j equals 1 to 4 of terms aj. Now note something that is very common in using these kinds of indices here, which is that we may change the index. So here I wrote the expression with n, here I've written the expression with j instead. That's very common in the use of indices. They're what's called dummy variables, and we can change them about as we see fit. Change the letters, it makes no difference. So it would be no difference in this summation if we wrote n equals 1 to 4 or j equals 1 to 4. We just have to remember to use n in here rather than j. Now, in this case here, we've also said, well, there are 4 terms in the series, so we've introduced another variable here, m, and m is equal to 4 for this particular series that we're summing. So we can also say we're summing from j equals 1 to m of this set of terms in the sequence to get the series. In this particular case, the answer to that summation is m times the sum of the first and last terms divided by 2. This is the average term that you have in the sequence. We can use this formula instead to add all these up, and we still get the answer 34. And this particular expression that I've put in the box here is a standard general result for the sum of arithmetic progressions of sequences. It's the answer to the arithmetic series. What does it all add up to? As a second example, we can look at the geometric series. In this case, we're looking at a series where there's a constant ratio between successive terms in the sequence. And we call that, as I said, a geometric progression or sequence. In this case, the nth term is given by the first term multiplied by this ratio r to the power n minus 1. So for example, the numbers 3, 6, 12, and 24 correspond with our a1 equals 3, a2 equals 6, and so on, to a progression like this, where the successive terms in the progression or sequence are a factor of 2 larger than the previous one. So r is 2, 6 is 2 times 3. And we have 4 terms altogether in this particular sequence, and we're going to call that m equals 4. And adding these all together gives the series, or the sum of the terms. So explicitly adding them up conventionally gives us 3 plus 6 plus 12 plus 24, which is 45. We can write that using summation notation from j equals 1 to 4 of aj. Note again, we're using a dummy index here. We've used j in this expression, we've used n up here, but it doesn't matter which of those indices we use. And we can also write this from j equals 1 to m with this explicit formula in here, again with j used instead of the number, or the index n. The result of that summation, the general result for geometric series, is this expression here, a1 times 1 minus r to the power m on the top over 1 minus r on the bottom. And of course that gives us the same answer when we work it out using this formula. R to the power 4 is 2 to the power 4, that's 16. And when we use this formula then we get 45 also. And just to emphasize that this is a useful general result for the sum of a geometric sequence, our geometric series here, I put a box around this result. The summation notation becomes even more useful when we have to deal with more complicated situations. We can extend the summation notation, for example, to handle the case where we might have two different lists of numbers, a1 through a4 and b1 through b3, where we might want to do something complicated like adding up all of the products. So a1 times b1 plus a1 times b2 plus a1 times b3 plus a2 times b1, and so on. Then we can use the following notation. Instead of writing out all of this set here, we can have two summations, one nested inside the other. So in this case, we might imagine we perform this summation first. For each value of j, we perform this summation over all of the k's from 1 to 3. So this expression and this expression with all of these numbers here are exactly equivalent to one another. And we remember that the order of addition does not matter, so we can add these up in any order we like. So it doesn't matter whether we put the j summation first and the k summation next to it. This would mean we're performing the k summation first and then performing the j summation. Or we could do that in the other order. Or we can, if we know what the ranges of j and k are, we may not have to bother to write them down. And sometimes, just to save space, we may bring the j and k up nearer to the axis here. Now, another extremely useful notation is the factorial notation. It's quite often the case that we need a convenient way of writing the product of successive integers. So we might be multiplying 1 times 2 times 3 times 4. Well, we have a simple way of writing that down. We write it as 4 factorial. And this is the exclamation point or the exclamation mark on your keyboard. The notation is obvious for most other cases, so 20 factorial, 36 factorial, and so on. But one special case is worth mentioning. It turns out to be very useful to define 0 factorial as 1. There are various formulae that come up when we're working with factorials, and in those formulae, it turns out that choosing 0 factorial to be 1 means the formulae are even more useful. One final notation we should mention is the product notation. This is like the summation notation, but instead of summing a set of terms, we are taking the product of a set of terms. So, generally, when we want to write the product of 4 successive terms like this, for example, a1 times a2 times a3 times a4, where those are specific numbers, then we can explicitly write them either multiplying them all out, obviously, or we can use this product notation. And just as we used the Greek S, or sigma, uppercase sigma, for the summation notation, so for the product notation, we use the Greek uppercase pi, and we make a nice big one here, just as we did for the sigma in the summation. And otherwise, the notation is similar, but we must remember that this is the product of all of the terms. So the product from j equals 1 to j equals 4 of aj, of course, is explicitly this. And for example, for all the integers, n greater than or equal to 1 at least, n factorial would be the product from p equals 1 to n of the number p in each particular case in the sequence.